Well, welcome back, everyone. Last day of class. It's been fun, and we're almost done. Hey, that rhymes. Don't get me started on poetry, though. I'll never stop. Okay. Well, what I'd like to do is to show you this maximum matching algorithm. I don't have the code listed here. Oh, yes, I do, actually. There we go. The maximum matching method. So here's the basic gist. It's like a dance. You've got rows here, you've got columns here. And if this is column J and this is row I, then you draw an edge between them if Aij is non-zero. Okay. So for an n by n matrix, you'll have n row nodes and n column nodes. So this is a very different kind of graph than we've used so far. It's a bipartite graph model. But any matrix can be viewed this way. So there's no edges between columns. That doesn't make any sense. So it's bipartite. It splits into two parts, and any edge goes only between the two parts. So that's the bipartite graph. To do this efficiently, of course, if you're at a given column, you may want, if you in the generic case, although it's different for here, is that if you're at a given column, you may want to go to a row, and then if you're at a row, you may want to look at its column, the columns it's adjacent to. So in other words, you may need to look at the matrix both by row and by column. So if necessary, you'd have a copy of A and A transpose. Every node has if you will, every row and every column has an adjacency list. So the way this works, there's several tricks that can be used. If we're at a specific column J, okay, then and we want to match where the goal is to match column J. So the algorithm at the very outermost level is just going to do for J equals 1 to n, or n minus 1 or 0 to n minus 1, whatever. So it's going to go through every column J, and it's going to do the match for J. Now, in the process, it may change the matchings of any previous column 0 through J minus 1, 1 through J minus 1. Okay, but it's not going to unmatch any previous column. It's like a dance. You might come in and say, "Excuse me, it's my turn." You kick somebody out, but then they immediately say, "Well, I'm not going to get kicked out from this dance unless you find me another dance partner." Okay, so that's what's happening here. So any previous nodes 1 through J minus 1 will remain matched, but their matchings may change. So the first thing to do to look at J is to see if there's a cheap match. That is, are any of its neighbors available, untaken? If they are, match them. So maybe this node is already taken by some previous node, but this one isn't. So take it. So this is matched. Now, this method has the property that once a row is matched and once a column is matched, they remain matched, but not necessarily to each other. So once you're on the dance floor, you don't get kicked off, if you will. And so what can happen is it may be necessary, we may find that all of the neighbors of J are matched. So there's nothing to do. So what we have to do is look backwards and say, well, who can I unmatch and modify to match node J? And that's the goal here. Actually, I should use K because that's what I've got here. This is node K here. Column K. However, when that happens, it's still useful to keep track of this cheap match notion. Because if I have to go back and say, look, all of node K's neighbors, all of these rows are all matched. Well, let's go back and see if we can modify the matchings of some of these rows, okay, and change this match. So I free this up and I match this with somebody else. Well, to do that, I'm going to have to look to see is this node adjacent to an unmatched neighbor? But I've already done that kind of computation before, and it's called I've looked. How can I say this? You're at a column J, and you want to go through and say, well, am I next to anybody who's unmatched? Okay, and if so, grab the next one. But you may have to come back and do this again. You may have to say, well, I want to change you, column J. So let's go back to you and ask, well, is there somebody else you're next to you could be matched to? Oh, let's go through the entire adjacency list and match to somebody else. But now think about that process. Once a row is matched, it never becomes unmatched. So you don't have to start at the beginning again. If you just keep track, look, here's the adjacency list of column J. And the last time you looked, you had to look this far and you stopped and you found someone who's unmatched, I'm sorry. So you match with that. Well, suppose next time you come along and say, look, I've got to change this. I can't dance with this row anymore. I got to go find another row. Let me find an unmatched row. I don't need to start at the beginning and look again, because any row that's matched will stay matched. Maybe to somebody else, but they're all matched. So if I'm looking for an unmatched neighbor, I'm not going to find it in this first part of the list. So we can keep track of where we left off, and that's called the cheap match. There's a pointer into each adjacency list called cheap, which is the last point at which we found the last match. So we can start there and keep going from there. And if we come to the end and cheap is all the way to the bottom, we know every neighbor is matched. And then in order to match J, we're going to look one level deeper in the graph to say, well, I'm going to go to a matched neighbor and say, hey, row, I'm going to kick you out, and I'm going to dance with you anyway, and you find another. That column it's matched to has to find another, and so forth. So every column then has this cheap pointer, a pointer called cheap of K, where K is cheap of J, where J is a column, will be a pointer into the adjacency list for column J, such that it has the property that any row in the first part of that adjacency list is already known to be matched. Now, there may be rows that are matched below cheap in the list, but I just haven't looked there yet. Okay. What this means is that then the process of looking for a cheap matched neighbor will only take time proportional to the number of non-zeros in the graph. It can't take more than that, because I'd never visit an edge twice. I'll look at a row and say, oh, you're already matched, increment cheap. Never come back to that edge again for that phase of the computation. So the cheap matches, even though that'll be happening in multiple places, like look here for a cheap match, go to column J again and look for a cheap match, go to column J and look again for a cheap match, again and again and again. But we're never starting over from scratch for that given column. So even though we'll revisit column J over and over again, perhaps, the cheap match the total work for the cheap match amortized will be total time proportional to the number of non-zeros in the A matrix. Okay, so what happens then if we come to a column K such that all of its rows that are adjacent to it are matched to obviously somebody else, not to K. So K is unmatched. Well, what we need to do is do a search of the graph, breadth first, depth first, it doesn't much matter. This is going to be a depth first search. It's a little bit more efficient, to find what's called an alternating augmenting path. So the alternating augmenting path says the following. Let me go to a matched row, who's my neighbor. Okay. This row is already dancing with somebody, and that's its partner, current partner, J1. So I1 excuse me, is in the adjacency list of column K, and it's dancing already with J1. And J1 is the match of I1. So there's a vector called J match. It's a function, if you will, that says given a row index, what column is it matched with? So what this depth first search is going to do, it's going to look at all potential rows. Okay, for all rows I'm next to, look at my neighbor row and then go immediately to this column and repeat the process recursively. So whenever you're at a row, you always go to, of course, if it's an unmatched row, you stop. That's the goal. But if you're at a row that's matched, you always go immediately to its matched column. So it's the columns that are taking the lead here in the dance, and the rows are just so. So anyway, at this column then, we can repeat the same process. Let's look at potentially all possible rows adjacent to J1, all of which then, in this diagram, would be matched. So I have to keep looking. Hopefully, eventually, I'll come to a column that's next to an unmatched neighbor. And this would then be the cheap match. This would be found only if I can look at the cheap list of J, 3 in this case, and say, oh, look, I found somebody. So this traversal here of checking to see if you're next to an unmatched neighbor uses that cheap pointer and advances it so that the next time you come back to J3, you won't have to start at this row I4 again. So the moment this is found, the entire depth first search of the graph stops. Now, in the worst case, starting at node K and trying to find node I4 may have to visit the entire graph. Okay, just to match node K, column K. And then to go to do K plus 1, it's possible you could traverse the entire graph. But in practice, that just rarely happens. There are a few pathological cases of matrices you can construct that causes the maximum matching to take that time. But it never happens happens in practice. And for those of which it does, you can modify this algorithm and randomize it. You don't have to visit the columns. This should be K here. You don't have to visit the columns of this graph in that given order. So this could be a random permutation of the columns. And so that's what the algorithm provides as an alternative, is if you come across a set of problems for which you hit this pathological worst case, you can randomize it. And then it will be the case that there's no bad graphs, there's just bad random choices. So it makes it more unlikely. I would do this permanently. I would do this always in practice, except that randomization leads to different results if you run the algorithm again, if you use a pseudo-random number generator. If you use a repeatable random number generator, even so, it's slower because you're bouncing through the graph irregularly. So it's slower in general, but much faster for a few cases. So it's an option. So here's the picture of this in terms of a matrix. You've got a box here with a zero-free diagonal, and you're trying to extend it by 1. So you're trying to extend it by column K. And you look at column K and you say, well, first of all, if there's any row down here, any non-zero here, well, that's the free match. But we don't find it. So we can't do that. So we go to the diagonal and go down and find it's harder to view in terms of, it's easier. This is simpler. This is hard to understand. Let's see. You're at this column. You go to that row. You go to its matched column J1, and you find another row, and you find its J2, and so forth. And this is the matrix picture of this. This is much simpler to understand, but this is here. And the idea is then, once you find these 4 elements, then finally you drop out of this box, and you say, hey, J3 would not have to be matched with I3. That's the match because that's on the diagonal. J3 instead could be matched with I4. Okay, so the idea, and this is going to be on the next slide, the idea is that once you find this alternating path, it's alternating because it goes back and forth between an edge which is not in the match set and an edge that is, not is, not is, not. And it ends with a row that is unmatched. So it's an augmenting path. It's alternating because it goes back and forth between unmatched and matched, unmatched, matched. And it's augmenting because the last node is unmatched and the first node is unmatched. And what can happen then is everybody can change dance partners. So in other words, if you look at this graph, you could say, well, there's an edge there. So these two could dance with each other. And so could those two, and so could those two, and so could those two. And that's the only, some people aren't willing to dance with other people. And the goal is to get everybody dancing. But, there's no edge J2 to I4. So they're not willing to dance with each other. But you want 4 couples to be on the dance floor. Well, there's the 4 couples. 1, 2, 3, 4. everybody's happy, everybody's dancing, whereas these three partnerships are broken, and now you have 4 couples, 4 matches on the dance floor, as opposed to 3. So on the next slide then, so these 3, 1, 2, 3 non-zeros are going to be ripped off the diagonal, and these 4 will be put in their place. So it extends the match by 1, and that's what happens on the next slide here. So here's the new graph, and there's the new match. So it's a depth first search, so it's a recursive algorithm, so we're in the end not going to want to use actual recursion, because the depth of the recursion could be n, and that could be 1,000,000, and that can cause stack overflow. And in fact, that's a source of a bug in an older version of MATLAB. It did a recursive implementation of this algorithm. So after I wrote this book, the MathWorks said, hey, we'd like to use your code in your book for this, because I wrote it non-recursively, and they wanted to fix their bug. So they used this code instead. Although this code, the only code I'm going to actually show you is the recursive version, because it's much easier to understand. The non-recursive version is printed in the book. You know, that's the actual DM perm in MATLAB. The code you're seeing in the book is actually now inside MATLAB. It's not just an implementation of what's in MATLAB. It is what is in MATLAB, the very code. But this code is not. You notice it doesn't have a CS underscore in front. Okay. So let's see. So here's the basic idea. We've got this JMatch function, which is an array of size m. We've got some workspace. This is the result. The matching is the result itself, and there's some workspace that we're going to use to mark the nodes, and also more workspace. So there's workspace to denote nodes that are marked, that are matched, and also the cheap pointers for every column. So that's there as well. And so we start off by saying that there's nothing that's been looked at for the cheap nodes. So cheap of j is AP of j, the column pointers. And I guess I don't need to have the matrix stored by row, so I only need it by column. Row I is matched with nobody. -1 means nobody. And then here's the algorithm right here. That's it, one line. That goes through all the column Ks and augments the match. And when we're done, we've got a maximum match. It's possible that there is no alternating augmenting path. So I could start at a node K, and it could be possible that if I traverse this from column K, and if I look and I look and I look, I don't find such a alternating augmenting path. Well, what that means is the matrix is structurally singular. There is no zero free diagonal. There is no matching where everybody is matched to everybody. Here in this particular diagram, there is. That's a 3 by 3 matrix, and there's a match of size 3. But there may not be such a match. There might be 2 in this case, whatever. This will determine that. The size of the match is what's called there's a name for this in MATLAB called the sprank, the structural rank, or the sparse rank of a matrix. And what the structural rank of a matrix is, it's an upper bound on the numerical rank. It's how many non-zeros you can stick on the diagonal maximally. And it has the property that you can't go any further than that. And that is then an upper bound in the actual rank of the matrix. So the augmenting function is very simple. It can fit on a slide if you do it recursively. It's a depth first search. And so each depth first search has to have a marking to know. I'm sorry, it's not. We don't need a marking to know whether or not a node is matched or not, because we know that nodes 0 through K are all going to be matched if it's found. And if it's not, it doesn't matter. It won't help us anything. But we need the marking to do the depth first search. You need to mark a node when you do a depth first search to not visit it again. And so that's what WJ is used. It's WJ is set to K if you've seen node J at the kth depth first search. So before we do the depth first search, we look to see if there's a cheap match. We just start at cheap and continue until we find it. And if we find it, that's great. That's flagged here. We find an unmatched row neighbor, and we're going to then use row I down here and do the match. And in any case, whether it's found or not, cheap is updated. So we never this code here, this loop here, then takes time, order, number of non-zeros in the A matrix. Even though it could be called used many, many, many times, this loop this innermost statement here is very quick. Then there's the depth first search, and then you've got to start over from the beginning, not from cheap. You've got to look at all your neighbors until it's found. And you look at a row and you say, well, first of all, is it marked? Is the column that I want to go to marked? Because this already does the alternating. So you're at a column J and you look at a row and you immediately go to its match, J match of I. Right there. But you skip it if it's already been searched in this depth first search. Otherwise, you try to find an augmenting path from column J match of I. So this is the entire algorithm here recursively used to find an alternating augmenting path. So you go from J here to a row that's matched to to any row, and then from that row to any column, to the column it's matched to, and then find an alternating augmenting path from that column. And then that J here is going to get placed on the stack. So this value of J then has changed. And so the call return stack is saving our path for us. And so that to unwind the recursion, all we have to do is this. If we find it, then we match I with J, and then return, and the augment will then recursively match everybody if we find it. It's amazingly simple once it's written, but it's very subtle in its recursion as to how it works. So that's it. That's the entire algorithm to find the depth first search. So once the depth first search is found, the next step in the DM param, DM stands for Dolmage Mendelssohn, name of two guys who developed this. Once a matrix has then a zero-free diagonal, then the strongly connected components are now unique, and now the goal is to find a permutation that puts the matrix into this form, where this is all 0 and this is non-zero. And if you want to see this, you can look at a function called CSDM SPI. It'll plot this picture for you for any given matrix. And I also have the same figure in my matrix collection. Come on. Why is this slow? All right, well, I'll let it freeze. Oh, there we go. And so once this permutation is found then, we can say do the LU factorization or QR factorization of each of these blocks. Now, the BTF is not as useful for symmetric matrices, because with a symmetric matrix you want to preserve symmetry. So if you preserve symmetry, that means this will also be 0, if such a permutation exists. And if the matrix is symmetric, it'll typically already have a zero-free diagonal. If it's not, it'll be symmetric indefinite. You want to use a symmetric indefinite solver. You don't want to destroy symmetry. This maximal matching destroys symmetry. It's a row permutation. Okay, you can't increase if you take a matrix and you permute the diagonal, you permute it symmetrically, you don't change the diagonal, you just reshuffle where they are. So this has to be an unsymmetric permutation. For a symmetric matrix, it may already fall into these strongly connected components, but the elimination tree will find this for you. It'll be a forest. the elimination tree will be a forest, so why bother? You'll exploit this already. So it's not really done needed for symmetric matrices, just for unsymmetric ones. But if we find let me see if I can find a matrix with this picture. Let's see. Here's one, for example. Okay, here's a Dolmage-Mendelssohn permutation right here, where this matrix here, it's already got a zero free diagonal, but it broke into a bunch of strongly connected components, of which many of them are just one by one. And so it found a matrix, in fact, where if it finds all one by ones, then the matrix is a permutation of a symmetric matrix. And this is then one. Each of these diagonal blocks are strongly connected components. Okay, so that's the block triangular form. And the Dolmage-Mendelssohn decomposition then combines these together. And but what I want to do is, in the last, let's see, I've got about 20 minutes. I want to talk about some other algorithms. And I meant to get some slides up. I'm sorry. I guess I didn't do this for the nested dissection ordering. So this is one. This block triangular form is not a heuristic. It will find the result. Okay. But then the heuristic says that, well, if I find such an ordering, and I can only have to factor the diagonal blocks, then this part right here remains unfactorized. I don't have to actually operate on this in my numerical factorization. I can just leave it alone and use block back substitution to solve this linear system. So I only have to worry about fill-in occurring here and here. So it tends to reduce the fill-in, but still ordering this matrix here then is an NP-hard problem. So we've seen two ways of ordering this matrix. We've looked at the minimum degree algorithm, AMD. There's also, for QR factorization in LU, sometimes it's useful to do a minimum degree ordering of A transpose A, because this bounds the Cholesky factor of the R or the U matrix in QR or LU respectively. So you could form A transpose A and call and use AMD on this graph. Or there's another algorithm, which we won't have time to explain, called call IMD, which operates on the graph of A, but treats it as if we're looking at A transpose A. And the way it does this is, if you look at A, and you remember those elements we talked about in AMD, think of A and think of multiplying A times A transpose. What happens is you get a collection of cliques in your graph. Every row of A specifies a clique in the graph of A transpose A, because you take this row, you can write the matrix multiplication down as a sum of outer products. This times this, plus the second times itself, plus the third times itself transpose, and so on. So if I've got 3 non-zeros here and 3 here, I create a 3 by 3 clique, all fully connected. So my graph of A transpose A starts as a collection of cliques. Well, the minimum degree algorithm is really great at representing a collection of cliques, sets of cliques. So why explicitly create all the cliques and then work on more cliques? This thing just starts with A as a collection of cliques. So every row is an element, and then every node, every column is a node. And we're done. And then we just have to do minimum degree then on this data structure. That's call AMD. But still, these are both minimum degree ordering algorithms. Now, they are the ones used in. Nobody now uses any other minimum degree ordering algorithms than these two actual codes. Really, I mean, these have now replaced, because of this approximate degree was so useful. These two methods are far better than previous minimum degree algorithms, but they sit on top of all these ideas from the previous algorithm. So it's just that one little increment that I added. It's really a modest change. But these are widely used in practice, these codes. But they're limited, okay? And I'll just say that bluntly. is that these minimum degree algorithms, as nice as they are with this minimum degree approximation and so forth, okay, is they tend to work well on some problem classes. They work well on very irregular structured problems, like the one on the screen here. Okay, it's a rat's nest. If you look at the picture of the graph, there's no obvious two-dimensional or three-dimensional structure to this problem. Right here. If you look at, on the other hand, at other graphs have very, very vivid two-dimensional or three-dimensional structure. For example, there's a helicopter here down at the bottom. Arg, I'm on the wrong page. You know, here's a helicopter, for example. It's very clear that this is a two-dimensional or three-dimensional object. It looks like some sort of sea creature. It's not. It's a helicopter. And for these problems, nested dissection works better. You take a graph G, and if it's got a two-dimensional, three-dimensional structure, you can lay it out on the plane. If it's a 2D graph, I mean it's a graph. If it's planar, you can lay it out on the plane, or you can lay it out on the helicopter, as you prefer. Okay, lame joke. Then what we do is we say, well, let's slice this graph in half. In particular, let's find a node separator. And a node separator is a collection of nodes that has the following properties. That any edge in the graph either exists on one side of the graph or the other, or just crosses one boundary but not, it can't cross both. So there's no edges that go crossing all the way across here. In other words, the node separator has the property that if it's a node separator, if you remove all the nodes from the graph, all in the node separator, and their incident edges, then the graph falls apart into two pieces. Okay. And so how is this useful? Well, if I call this component A1 and call this A2, and I call this separator S, then what happens and if I order A1 first, then A1 is some kind of arbitrary structure. And if I put A2 next, then A2 has edges within itself. But there's no edges between A1 and A2. The nodes in A1 and A2 have no edges between them. So this is entirely zero. And then the separator, which is hopefully small, then has edges to anybody, including within itself to A1 and to A2. So the graph looks like this. If you do nested dissection ordering, if you find one node separator, then you get this structure here. Now, when you do a Cholesky factorization on this matrix, these large regions of zero are preserved. And that's the idea of the fill reducing ordering, is that all of these zeros these zeros do not go away. Okay, now the question is, so when I factor A1, I get fill in here and here, and I get fill in within A1, but not here. So now the question is, recursively, how do you order A1? I've just put all the nodes in there. Well, is there a better ordering of A1 itself? If I permute A1, no matter how I permute A1, these will remain zero. If I select all my pivots from A1, these blocks remain zero. So then the question remains, well, how do you select A1? Repeat recursively. Okay. So you've got this graph, you've found the node separator, and so let's then remove it. Let's pretend that now this is our problem. Then the question is, well, how do you order that? Oh, slice, you find another node separator. You slice it into two parts. So this thing becomes this. And you do that with A2. And you repeat until this graph becomes small enough such that it has no fill, it's 1 by 1, 2 by 2, it's dense, whatever. It has no reasonable separator except the entire graph. That's a dense graph. Or, alternatively, these methods can be combined into a hybrid approach. I mean, maybe this is 1,000 by 1,000, and you decide for small graphs under 1,000 nodes, how do you order that? Well, let's use minimum degree. Minimum degree works very well for small graphs. Very good quality. as well. Very fast and very high quality. Nested dissection, on the other hand, is slower than minimum degree. And it can give better quality. But the place it gives better quality orderings is typically only for large three-dimensional graphs, large graphs that come from 3D simulations. For those, nested dissection is almost uniformly better than minimum degree. So if you have and typically you know that. You know you're modeling some three-dimensional problem. Unless you're just grabbing a matrix out of a collection like this, you don't know where it comes from. That's why these visualizations are really helpful. You can look at that and say, ooh, that looks like a 3D object. You know. And that gives you then the nested dissection ordering. Now I don't have much code in the book that computes a nested dissection ordering. There is such a one. It's based on the maximal matching method. Okay, and I don't really have time to explain how it works. Because it requires more details in the DM perm, which I've not explained. What happens with DM perm when you have a rank deficient matrix is very peculiar, and there's some interesting properties of it that I don't have time to explain. And it's those properties that are used to find this find a node separator. It turns out, though, that using DM perm to find node separators is not really a great quality solution anyway, although it makes it real simple to write a nested dissection algorithm in MATLAB in about 3 lines of code, as I've got here in the book. The ordering quality is not so great, but the recursion is very simple itself. You just to get this ordering. The hard part is, given a graph, how do you find a node separator? That's the hard part. So much so that, in fact, this is an open research topic still. I mean, there's codes out there that do it. I'm working with a student to look at edge separators. He's also going to look at node separators. Methods for finding this are still open. There are some open research issues in AMD, in the approximate minimum degree. Okay. In particular, what happens if you have a node that's dense? It's connected to every node. And when you have in minimum degree, when you have a node that's connected to every node, then you have to touch it every iteration. If you touch it every iteration, then you also have to touch its neighbors. So one dense node in the graph causes the time complexity to be n squared. Could you move the slide over graph over to put camera over here, please? Okay, well, nobody's watching, I guess. There we go. Good. Thank you. So this one node causes the minimum degree ordering algorithm to take n squared time. So what AMD does in the code is it looks for these nodes and removes them first, because if this is a dense node, it will put it last in the ordering. Why bother to try to figure out where it goes? So these are easy to detect. The hard part in AMD is detecting nodes that are not quite dense. They're fairly dense, not enough to cross a threshold that says you get rid of them, but small enough that you have to consider them during the ordering, but still dense enough to cause the runtime to go really high. So that's the hard part. And how do you avoid those? And in fact, those graphs really do occur. Those matrices really do occur, and they tend to occur in optimization problems. So I've got a colleague out in California, Ed Rothberg, who's wanting to figure out how to make the minimum degree algorithm work better in the presence of such collections of many not quite sort of pseudo half-dense nodes. And you've got a lot of them, they'll cause the ordering time to really jump high. And we'd like to try to see if we can avoid that. If you remember, I did a plot of comparing relative performance. So this is the time for the simple Cholesky algorithm. This is the up-looking Cholesky, which you see in the book, over the time for a supernodal solver. 1 means the same time. A time, say 0.5, says that the simple code is faster than the supernodal code. And a time of 2, and this is going to be a log plot then, a time of 2 says that the supernodal algorithm is twice as fast, and 4 and 8 and so forth. So this means over here that the supernodal algorithm is 8 times as fast. And the x-coordinate is the flop count divided by the number of non-zeros in the matrix L, the resulting matrix L. Both of these results here can be pre-computed in the symbolic analysis because you get the column counts. And the sum of the column counts is the number of non-zeros, and the sum of the column counts squared, the sum of the squares, is the flop count. Okay, so this is easy to get. And then you plot a bunch of matrices. And it looks like this. Almost uniformly along some nice S-shaped curve. And the threshold is about 40. And it's so accurate that I don't really provide the user much option. There is an option in the code that you can change this threshold to 40. You can also force it to do this method or the other method. But nobody bothers to, because the selection is so good that automatic. However, with this curve, I mentioned a while back that there are a few outliers here. That their performance is below what you would expect them to have in this relative computation. In other words, the runtime of the two methods, super or simple the up-looking method or the supernodal left-looking method, the runtime is more similar than you would expect. Okay. The reason is this runtime, this total time, includes the ordering time. And if the ordering time is really, really high, they both use the same minimum degree ordering. So if the minimum degree ordering is really, really high, then the numerical factorization is noise. Okay, well that's what's happening with these two. These two matrices are matrices that don't have, they have some completely dense nodes. Okay, but they're not detected, or they're not quite dense enough to be detected. You can play with the knob and detect them and improve the ordering, improve the time, but it makes the ordering worse, and so there's no really nice clean solution. And these outliers are not because of the numerical factorization. They're because of the symbolic pre-ordering. And they're here because the AMD algorithm is very susceptible in terms of its runtime to the existence of these nodes. And most matrices don't have these nodes, but there are some problem classes that do, and the ones that do tend to be coming from linear programming or nonlinear programming. You want to solve an optimization problem. To solve that, you need to factor a matrix. You get this coefficient matrix. You need to solve a sequence of linear systems. And finding the ordering can be painful because of this one glitch. And but maybe for these matrices, nested dissection doesn't work too well. Minimum degree is the method of choice, but it's slow. And you can see it here in the results. They actually do happen. So these methods are not perfect by a long shot. I mean, we have nested dissection is a heuristic, and it's very slow compared to minimum degree, typically, except for a few off-ball cases like this. Nested dissection doesn't always give you the best ordering. It's really not great for generic matrices. It's not any better than minimum degree for two-dimensional graphs, planar graphs. It really shines for 3D problems from 3D simulations. And usually you know that your graph has such property because you know what you're simulating. You know you're doing some finite discretization and partial differential equations on a 3D volume. Okay, I'll use nested dissection, and it'll be better. So, again, nested dissection and minimum degree are both heuristics. You can combine the two. All right, I explained how that can happen. You can do nested dissection at the coarser level, and as you get down to the finer graphs, you just punt over to minimum degree and order the subgraphs with minimum degree. Many ways of finding node separators out there. They work well in practice, but they are not really fast. So minimum degree typically is faster. And so there's still some open questions in nested dissection. Is can we get these node separators computed faster than we're getting them right now? So can nested dissection compete in runtime with minimum degree? Because this thing is so fast. In fact, this is really almost typically, except for these outliers, an absurdly fast algorithm. In the sense that the time complexity of this algorithm it does actually have a bound. See, the graph is changing with minimum degree. It's changing very dynamically. You got to visit your neighbors and but the graph is changing. So what's the time complexity? The time complexity actually has a very loose bound, which is not unlike the total flop count. I mean, it's different than the flop count, but it's on that order of magnitude. The flop count to do the Cholesky factorization. Well, that's horrible. That's a very high amount of time. But you see, it never reaches that in practice. Ooh, well, never. Ha-ha. Okay. It can get really painful here. But most of the time, it doesn't. So typically, it's fast. And typically, in fact, what I've done is I've tested all these thousands of matrices and tried to draw a plot. And the runtime of the minimum degree algorithm maybe in practice looks something like this. It's slightly superlinear, 1.1, 1.2. The number of non-zeros in A raised to a very small power. I don't know. I think it's roughly 1 or 1. I think it's almost essentially 1, or actually it's 0.9. It's even sublinear, which is kind of weird. It's got to visit all the non-zeros in the graph. Okay, so this is a very noisy plot. There's no really smooth answer here. For matrices, this is the case for matrices that are very regular, like 2D or 3D discretizations. For irregular graphs, it can be higher than this, and the data is more noisy. But if you plot this versus, if you take the minimum degree ordering runtime, and you plot it versus the number of non-zeros in L, then it's clearly sublinear. It does this. That's a log-log plot. I mean, there's a few outliers here, but typically it's sublinear in the number of non-zeros in the factors. Which is intriguing, actually, if you think about it, because the minimum degree ordering algorithm is actually giving you this count. It's actually, you're creating these elements. Every time you create an element, you're looking at its adjacency in the L matrix, in a concise representation with cliques. So if you sum up the node of least degree, you pick a node of least degree, and you not eliminate it. If you actually compute that degree and sum up the degrees, you get the count of L. But it's sublinear in L, the total time. In other words, you're not actually visiting all those neighbors in the minimum degree algorithm. So it's asymptotically fast in that sense. It takes time less than what it's actually simulating. Okay, so it's more like linear in the graph A itself, not the graph. This would be the elimination graph. If I were to represent the elimination graph, then it would have to take at least this amount of time, because you'd see every one of those edges. You'd see them. So there's a lot of interesting open questions with ordering algorithms. Then, are there better methods out there? They're all heuristics. Are there better runtime? I mean, minimum degree does not have a very tight bound. Nested dissection doesn't have a very good bound either. As I said, and they're all heuristics, so are there better methods? So I've come to the end of class, and normally what I like to do is kind of put it all together and show you what MATLAB does when it's presented with the matrix. It's got to solve it. So you can read that in the book. That's on page 140. It goes through a whole suite of methods, many of which now are covered in the book. We've seen triangular solves. We've seen LU factorization. We've seen matrix multiplies and things like that as well, basic operations. We've seen a lot of different factorization methods. We've seen a whole lot of graph theory. Okay, really, as I said at the beginning of the course, that what is this course? This is a course on graph algorithms more than anything else. And there's one of my favorite graphs. Okay, and you're working on this as if it's a matrix, but really underneath it's a graph. And all the things you do on this thing, looking for edges and paths and cliques and trees and separators and subtrees and subgraphs and cliques. Did I say cliques? Oh, those aren't matrix notions. Those are graph notions. These are all graph algorithms, and the numbers sort of go along for the ride, and we happen to be in the process solving a linear system. That is sparse direct methods. So with that, I'll close, and it's been a fun semester. And the project, of course, is due shortly. If you have any questions, you can ask me after class. And it's been a pleasure. Thank you.